Hi, we're going over lesson 3 of unit 7 for chemistry, and in this lesson we'll focus on colligative properties as well as boiling point elevation and freezing point depression. For our lesson objectives, students will learn how to solve for the freezing point depression and boiling point elevation of a solution. Let's get started. We're going to go ahead and start our lesson by discussing colligative properties. What exactly are those? A colligative property is one that depends on the number, not the identity of the dissolved solute. So keep that in mind, is the quantity, how much solute is there, that really affects the way it behaves. A great example of colligative properties is when you see salt being spread on roads when it's snowing. What that will do is to go ahead and lower the freezing point, and as it lowers it, therefore it allows the snow to melt. That's why salt is added to the roads in places where it snows. Now, what are the three colligative properties? So we're going to talk a little bit about each one of these. There's vapor pressure lowering, boiling point elevation, and freezing point depression. For boiling and freezing point elevation and depression, we're actually going to do the calculation to solve for those. For vapor pressure lowering, let's go ahead and talk about, first of all, what is vapor pressure? So let's say that you have a container and it's got water in it. Some of that water will go ahead and evaporate. So in the picture below, the water is represented by the little blue spheres right there. So here's some water molecules there and there and there. All right, if we were to go ahead and cover this up, those water molecules will stay in the vapor phase and they will produce pressure. That's what we refer to as the vapor pressure. All right, so how does adding a solute affect the vapor pressure? Well, on the left-hand side, we have a pure liquid, and pretend that it is covered. So that's supposed to be a lid on the top. And what that will do is going to go ahead and keep the water vapor there. Now, how many water molecules do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. 8 water molecules above the surface of the water. On the right-hand side, if you look closely, we have a solute added here in this pink color. And again, pretend that we have a lid on top. So what's going to happen? Well, we have only 5 molecules above the water surface. All right, so 8 versus 5. Why do we have less water molecules when there's a solute present? Because the water will attach itself to the solute molecules through the process of solvation. So since the water molecules are attached to solute, they're unable to evaporate and go to the gas phase. So therefore, there's less water molecules in the gas phase. All right, what does that do to the pressure? Well, on the left-hand side, when we have just pure water, we have more molecules, and more molecules represents more collisions of those gas molecules against the walls of its container. So therefore, that increases the pressure. On the other side, on the right-hand side, we have less water vapor molecules. So therefore, less molecules, less collisions, and therefore less pressure from that water vapor. So adding the solute will reduce the surface, the vapor pressure, because there's less water molecules in the above the surface of the water. Now, the presence of the solute will elevate the boiling point. So instead of boiling, let's say water boils at 100, now it might boil at 101, 102, so it'll elevate it. But it will also depress the freezing point. So instead of water freezing at 0 Celsius, it's going to go ahead and maybe freeze at something lower, maybe -1, -2, -3. In this phase diagram you see here, the black line represents just pure water, and it is labeled right here, pure liquid solvent. What will adding a solute do is going to go ahead and expand the liquid section. So notice that here, this line where it used to be here has now moved to the left. So it has depressed the freezing point, and the boiling point here at 1 atm, so normal boiling point, now has been moved over here. So it has elevated the boiling point. All right, so what we're going to go ahead and do is now do the calculations to figure out if we add 1 gram of salt or 2 grams of salt to 100 grams of water, how much will the boiling point increase and how much will the melting point or freezing point decrease? All right, to begin that conversation, we have to start with the Van Hoff factor. All right, so the Van Hoff factor measures the number of particles in the solution. All right, so when molecules are connected by covalent bonds, the covalent bond is a very strong bond. So when they're placed in water, they are not going to separate. So if you have a lot of covalent bonds, those molecules will not separate. So you get a Van Hoff constant of 1. On the other hand, if you have an ionic bond, the ionic bond is weak. when placed in water, that ionic bond is going to break. So that molecule is going to break into several pieces. Now, quick reminder, how do you know if a molecule has a covalent bond or if an ionic compound has an ionic bond? It has to do with the molecules that are, or the atoms that are attached to each other. For example, two nonmetals will give you a covalent bond. So the Van Hoff constant will be 1. If you have an ionic compound, then that is a metal with a nonmetal, they'll have an ionic bond. It's going to separate. So now you're going to have a Van Hoff constant more than 1. All right, so for example, salt that has a metal with a nonmetal. So here we go. Here in the table, the metals are right here in this purplish color. And so sodium will find it in this corner right here. And on the other hand, chlorine is right here. You can't really see it with my red on red, but those are the nonmetals. So we have a metal with a nonmetal, then they will form an ionic bond that will separate in water. So the Van Hoff constant is more than 1. And again, what if you have two nonmetals that's a covalent bond? They're going to stay to each other. Now, what we should do is go ahead and go over the rules a little bit further. So let's see. Compounds with covalent bonds do not dissociate in water. That means break apart, dissociate. Therefore, their Van Hoff constant is 1. Compounds with ionic bonds will dissolve or dissociate in water. Therefore, their Van Hoff constant is found by counting the number of subscripts in that compound. So let's go ahead and take a look at some examples. So in example 1, they ask you find the Van Hoff factor for each of the following. So let's start with the first one, that is glucose, C6H12O6, carbon, hydrogen, and oxygen. They're all covalent bonds. All of them are covalent bonds. So I can go ahead and say, well, therefore, the Van Hoff factor is just 1. That'll be the answer for that molecule. Let's find a couple more just like that. The third one here, we have CH3OCH3. Again, we have carbon, hydrogen, and oxygen. All of them are nonmetals as well. So therefore, if they're all nonmetals, the Van Hoff factor is 1. And let's see, any other ones? Yes, the second one, NF3, nitrogen and fluorine. Both are nonmetals. So therefore, the Van Hoff factor is 1 as well. All right, now let's get into some other ones. We're going to jump around a little bit. Let's go ahead and talk about this one, KF, that is potassium fluoride. Potassium fluoride is made of metal with nonmetal. So will it separate? Yes, they will, because they have an ionic bond. So they're going to separate into how many parts? The answer, well, there's 1 K, there's 1 F. So it's going to separate a total into 2 parts, 1 K and 1 F. All right, so the Van Hoff factor for potassium fluoride would be 2. Right above it is K2O, so that will be potassium oxide. And again, we have a metal with a nonmetal. They will separate, because that's an ionic bond, metal, nonmetal, into how many pieces? Well, we're going to go ahead and count the subscripts again. 2 Ks, 1 O, so the answer will be 3. The Van Hoff factor for potassium oxide will be 3. And let's jump around some more. Down here, let's take a look at iron 3 oxide. Iron is a metal, oxygen is a nonmetal, so it's an ionic bond holding those two atoms together. You put them in water, it will separate, it will ionize. So how many parts will it ionize into? 2 irons and 3 oxygens. Put them together, that's a total of 5. All right, so you get 5. The Van Hoff factor for iron 3 oxide is 5. All right, now let's increase the difficulty. The substance right above it is NaOH, sodium hydroxide. So for sodium hydroxide, NaOH, the answer is a little bit more complicated. Here we're mixing covalent bonds with ionic bonds. So for example, between oxygen and hydrogen, that bond right there, that is covalent because both of those are nonmetals. But the bond between sodium and oxygen is ionic because you have a metal, which is the sodium, with a nonmetal, which is the oxygen. So it will split, but only between the Na and the O. The O and the H will stay together. So therefore, if I ask you what's the Van Hoff factor, there's only 2 pieces, the Na and the OH. So the answer for the Van Hoff factor would be 2. Lastly, let's go ahead and take a look at sodium phosphate here on the bottom left side. Sodium phosphate is going to split into only 3 parts. Now you might look at that and say, how do you come up with that number, 3? All right, it's very similar to sodium hydroxide where you have the phosphorus and the oxygen, two nonmetals, so they're going to stick together. So all of this, the PO4, think of it as just one piece. Now between the sodium and the phosphate, that is an ionic bond, so that will split. But we got two sodiums, and remember the PO4 is only stays as one piece together, so there's a grand total of 3 for the Van Hoff factor for the sodium phosphate, 3. All right, so those are some examples on how to solve for the Van Hoff factor. Once you put it into the formula, you're looking for a symbol that looks like this, a lowercase italicized I, and that will be the Van Hoff factor. So here's our formula for the freezing point depression. Freezing point depression is calculated by the following. Fp for freezing point is equal to the normal freezing point of the substance minus I times M times Kfp. All right, now what are all of those? NFP is the normal freezing point, and for water, that is 0 degrees Celsius. M is molality, I is a Van Hoff constant, and Kf is the constant for the freezing point. And if we're using water, it's going to go and be 1.9. If we're using a different substance, well, it will be a different value. But for our class, we're only going to go ahead and use water. So there's only really two variables here, the I, which is the Van Hoff factor, and the molality. All right, as far as the other values, the NFP, it is 0. You're going to go and substitute for the normal freezing point using water. And for Kfp, for the constant for the freezing point, will be 1.9 again for water. And those will be constants. So only two variables one more time are the Van Hoff constant or the Van Hoff factor, you can call it either way, or the molality. Let's go ahead and do some examples now and use that formula.
In example 2, we're asked the following question. What is the freezing point of a solution made from 124 grams of Na2O, sodium oxide, and 0.5 kilograms of water? So in this problem, to solve for the freezing point, we're going to go ahead and need the molality. So that's going to be our very first step. And to solve for molality, we're going to need to change the 124 grams to moles and then divide it by the kilograms of water. So let's go ahead and start there. So our very first part, I'm going to go ahead and get the molar mass of the sodium oxide. All right, so sodium oxide, Na2O, then we got 2 sodium atoms and 1 oxygen atom. The molar mass of sodium is 23 and oxygen is 16. So it's going to go ahead and give me 46 times 16, 1 times 16 is 16, giving us a grand total of 62 grams per mole. Now that is the molar mass of the sodium oxide. Now we're going to use that number to go ahead and change the 124 grams to moles. So it will look like this. Here's my given, 124 grams of Na2O. And we're going to put 1 mole in the numerator and our molar mass in the denominator. So multiply 124 times 1 divided by 62. That goes ahead and gives us 2 moles. All right, now we have the moles. I can go ahead and use that to solve for molality. Molality is moles over kilograms of solvent. So it's going to go ahead and look like this. My 2 moles divided by my 0.5 kilograms of water. It's going to go ahead and give me a 4 molar solution. All right, now that I know that, I can go ahead and plug it into the formula for boiling point, and it's going to go ahead and give us the answer for, in this case, actually freezing point. So freezing point is as follows. The normal freezing point, which is, I'll just put it NFP, minus the Van Hoff constant times the molality times the constant for the freezing point. All right, so let's start plugging on the values. The normal freezing point of water is 0 degrees Celsius minus the Van Hoff constant. All right, Na2O, the sodium oxide, is a metal, sodium, attached to a non-metal. So when you place it in water, it's going to go ahead and ionize. All right, so the Van Hoff constant is going to be 3 because it's going to split up into 3 pieces, 2 sodiums and 1 oxygen. So for the I, our factor right there is going to be 3. Molality, we just got it, 4 molar. And the constant, it is 1.9 degrees per mole. Alright, so that will be our formula. Next, we're going to go ahead and multiply everything on the right. So it's going to be 3 times 4 times 1.9 gives us 22.8. So our freezing point is going to be 0 degrees Celsius minus 22.8 degrees Celsius. So our final answer is going to be negative 22.8 degrees Celsius. That is the freezing point for our 4 mole solution of sodium oxide. Let's go ahead and take a look at another example. In example 3, they ask you what is the freezing point of a solution made from 720 grams of C6H12O6 as glucose and 2 kilograms of water. So very similar problem. We're going to end up doing much of the same, where we go ahead and you need to find the molar mass first. Then we're going to use that to convert the 720 grams from grams to moles. And then we're going to find the molality, plug it into the formula, and solve. Alright, so again, first step, gotta get that molar mass. So C6H12O6 glucose, let's see, we got 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Alright, that's how many of each we got, 6, 12, 6. Now we're going to go ahead and multiply and times their mass from the periodic table. Carbon is 12.0, 1.0 for hydrogen, and 16.0 for oxygen. So we go ahead and we multiply. We have 6 times 12. It's going to go ahead and give us 72, 12, and 96 for a grand total of 180 grams per mole. So that's my molar mass of the glucose. Next, I use that molar mass to go ahead and change my 720 from grams to moles. Alright, so here's my given 720 grams of glucose. Now I'm going to go ahead and convert them 1 mole in the numerator, 180 grams in the denominator. So that's going to go ahead and be 4 moles. Alright. Now we have our 4 moles. I need the molality. Molality is moles over kilograms of solvent. So it's going to go to be 4 moles over the kilograms. It is 2 kilograms of solvent. So 4 divided by 2 give you 2 molar. That is our molality. Alright, so we're going to plug it in right there. Next to it we have the I, which is the Van Hoff factor. This molecule, it's all of the atoms are nonmetals. Carbon, hydrogen, oxygen are all nonmetals. So therefore they have a covalent bond between them, so they're going to attach to each other. It's not going to ionize in water, so stay as one piece, so therefore our Van Hoff factor for it is just 1. Alright, plug it into the formula. Freezing point is, normal freezing point of water, 0 minus 1 for the Van Hoff factor. The 2 molar. And the constant for water is 1.9 degrees Celsius over molality. We go ahead and put this into our calculator, and it gives us the following answer. So it's going to be 1 times 2 times 1.9 will give us negative 3.8 degrees Celsius. That will be the new freezing point when we add 720 grams of glucose to 2 kilograms of water. Next, let's move along to example 4. Here they ask you, what is the freezing point of a 4 mole NaCl solution? So we are adding salt, sodium chloride to the solution, and it has a molality of 4 molar already. Now notice that in this problem, we already have the molality, so we can skip figuring out the molar mass, and we can figure out the moles, we don't need to, and the molality is already given to us, 4 molar. So we can go ahead and start at this point right here. So let me go ahead and erase the previous problem. And again, they're already giving us the molality, so that's all I need. The Van Hoff factor for NaCl, that one, let's take a moment to talk about it. NaCl it is Na is a metal, Cl chlorine is a non-metal, so it's an ionic bond between them. So when you put them in water, they will ionize, they will separate. So it's going to dissociate into two parts, one Na, one Cl, so our I equals 2. So now I'm going to plug it in here. Freezing point is equal to 0 degrees Celsius for the normal freezing point of water, minus 2 for the Van Hoff factor. Molality is given to us. The molality is 4. And the constant 1.9 degrees Celsius. Alright, so now we plug it into the calculator. And we're going to get the following. Freezing point is negative 15.2 degrees Celsius. Alright, that's our answer for example number 4. Next, let's go ahead and take a look at example 5. In this one, they ask us the question, how many grams of potassium chloride, KCl, are needed to depress the freezing point of 250 grams of solution to a temperature of negative 19 degrees Celsius? Alright, so this problem is a little bit backwards where they're giving you what we want the temperature to be, so therefore, how much of the KCl should we add? Alright, so let's start with what we do know. We know the freezing point that they want, the depressed freezing point is going to go ahead and be negative 19 degrees Celsius. Normal freezing point of water is 0 degrees Celsius. We know we have KCl, the potassium chloride, and for potassium chloride, the Van Hoff factor for it is going to be 2 because potassium is a metal and chlorine is a non-metal, so therefore it's going to split into 2 parts. Alright, so I'm going to put that here. The molality we don't have, but we do have the constant 1.9. Alright, so what we're going to go ahead and do is solve for the molality now. Alright, so let's see. We're going to go ahead and have negative 19 degrees Celsius. 0, well, this 0 minus this, so it just goes negative. 2 times 1.9 will give you 3.8 molar. Alright, so that's what we got. Now I'm going to go ahead and divide it both sides by negative 3.8. That will cancel out, giving me a molality of 19 divided by 3.8, 5 molar. Alright, now that we have that, we're going to go ahead and figure out how much volume we have. Alright, the volume we have 250 kilograms of solution. Alright, now, formula for molality though calls for moles over kilograms. Alright, so the solution is 250 grams, we need to change them to kilograms. So, before we can plug them in here. Then once we do that, what we're going to do is multiply kilograms times the multiply the molality times the kilograms to get the moles. So it'll end up looking like this. Kilograms times molality equals the moles. Alright, so kilograms, again, is 250 grams. To change into kilograms, you're going to go ahead and divide it by 1,000. So that becomes 0.25. So it's going to be 0.25 kilograms. Multiplied times the molality that's given to us, it is 5 molar. And that gives us 0.25 times 5, 1.25 moles of the KCl, of the potassium chloride. Now, we want to know not the moles, but how many grams that is. So now we're going to go ahead and convert the moles back to grams. Moles. Alright, so what we're going to need is the molar mass of the KCl. So let's go ahead and take a moment to solve for that. KCl, there's 1K, 1Cl. Molar mass of Cl is 35.5. Molar mass of potassium, it is 39.1. So we go ahead and multiply 39.1. Well, it's times 1, it's the same value. 35.5. So we're going to go ahead and add them up. 35.5 plus 39.1 gives us 74.6 grams per mole, and that is the molar mass of the potassium chloride. So I'm going to go ahead and put that here. And now I can go from moles to grams and get our answer. So that's going to go ahead and be 93.25 grams of the potassium chloride that we need to dissolve in the 250 grams of solution to go ahead and get a depressed freezing point of -19. All right, that is example 5.
Next is how to solve for the boiling point elevation. We know that pure water, it will boil at 100, but if we start adding a solute into the water, it's going to go ahead and elevate the boiling point. So it might boil instead of 100 at 101, 102. So how do we solve for that? Here's our formula. So boiling point elevation is calculated by the equation BP for boiling point is equal to the normal boiling point plus I times M times KBP. What are those? Well, NBP is the normal boiling point of water, and water normally boils at 100 degrees Celsius. M is molality, I is the Van Hoff factor or Van Hoff constant, and KBP is the constant for the boiling point, and for water, it is 0.5. Again, the NBP for water is 100 degrees Celsius, and the KBP is going to be 0.5. Those are going to be constants since for our class, we will only be using water. If we were to change the solvent to maybe alcohol or another substance, then you'll have different values. But again, for our class, we're only going to go ahead and use water. So those will be constants. NVP, normal boiling point, 100 degrees Celsius, and KVP, 0.5 degrees Celsius per mole. So now let's go ahead and use this formula and solve some problems.
In example 6, we're asked the following question. What is the boiling point of a solution made from 170 grams of NaNO3, which is sodium nitrate, and 500 grams of water? So we're going to begin this problem by getting those 170 grams of the sodium nitrate and switching them from grams to moles. First, we're going to need the molar mass. So for NaNO3, we're going to find the molar mass of this compound. So it's going to be Na, there's only one atom, and nitrogen 1 and oxygen 3. Next, we're going to go ahead and multiply them times their mass from the periodic table. Sodium's 23, nitrogen is 14, and oxygen is 16. So that's going to go ahead and give us 48. Next, we add them all together, and we get 23 plus 14 plus 48 gives us 85 grams per mole. So I got the molar mass of the compound NaNO3. Now I'm going to use that to change my 170 grams from grams to moles. So I'm going to write my given 170 grams of the NaNO3, and we're going to go ahead and put 1 mole in the numerator, and in the denominator 85 grams. That way the grams will cancel out, and that's going to go ahead and give us 2 moles. Alright, so next what we're going to do is we're going to get those grams and switch them to kilograms. So it will look like this. 500 grams of water, for every 1 kilogram there's 1,000 grams, so that's going to give us 0.5 kilograms. Now we can go ahead and solve for the molality. Molality is moles over kilograms. So I got my moles here, I got my kilograms. So we have 2 moles over 0.5 kilograms. So that's going to give us 4 molar. Alright, so that is the concentration of the solution. Now we can go ahead and plug it into the formula for boiling point. Boiling point is equal to the normal boiling point of water plus the Van Hoff constant times the molality times the constant for the boiling point. Alright, so the normal boiling point of water is 100 degrees Celsius plus the Van Hoff constant. Alright, so now let's go ahead and take a look at this molecule. It's got 3 atoms in it, sodium, nitrogen, and oxygen. And though sodium is a metal, that will dissociate. Nitrogen and oxygen are both non-metals, so they're going to go ahead and stick to each other. So the Van Hoff factor for this compound is going to be just 2. Alright, molality we just got, it is 4. And the constant for the boiling point for water, 0.5. Alright, we plug all of this into a calculator and it'll give us an answer of 104 degrees Celsius. And that is our boiling point, our elevator boiling point, when you have 170 grams of sodium nitrate in 500 grams of water. Let's go ahead and take a look at our next example. In this one, they ask us, what is the boiling point of a solution made from 234 grams of NaCl, that's table salt, and 2 kilograms of water? All right, so very similar problem. And again, we're going to begin by figuring out those 234 grams. How many moles is that? So that'll be our very first step. So we're going to need the molar mass of the NaCl to solve for that. So we have NaCl, there's one of each. Their mass is 23.0 for the Na and 35.5 for the Cl. So it'll give us 58.5 grams per mole. Alright, so that is the molar mass of the sodium chloride. Now we're going to go ahead and use that to get those 234 grams, so switch them to moles. So I'm going to write down 234 grams of NaCl, put 1 mole in the numerator, and the molar mass excuse me, on the denominator. So 234 divided by 58.5 gives us 4 moles. Alright, so now we got the moles. Notice we also got the kilograms of the solvent. So all we got to do to solve for molality is divide the moles over the kilograms of solvent. So it will look like this. 4 moles over 2 kilograms is going to give us 2 mole. Now that we have that, we can plug it into this formula for the molality right there. So it's going to be boiling point is equal to the normal boiling point of water, which is 100 degrees Celsius, plus the I, that's a Van Hoff constant. Let's take a look at NaCl. Na is a metal, Cl is a non-metal, so therefore they're going to ionize. So I is going to be 2. Molality, 2. Constant for the boiling point of water is 0.5. So it's going to give us a boiling point, an elevated boiling point of 102 degrees Celsius. Alright, that's the answer for example 7. Next, let's go ahead and take a look at example number 8. In this one, they ask you is, what is the boiling point of a 3 molar C6H12O6 solution? That's a glucose solution. So we have a 3 molar solution. You want to know the boiling point. Notice that they give us a molality already. So this first part is already done for us, which is what we used to figure out the molality. So let me erase the previous problem. And again, they gave us a molality. So now we can go ahead and start from this point. First of all, boiling point, our elevated boiling point is equal to the normal boiling point of water, 100, plus I, in this scenario, carbon, hydrogen, and oxygen, they're all non-metals, so therefore they have a covalent bond holding them together. So it's going to be just factor of 1 for the Van Hoff factor. Alright, the molality is given to us is 3 molar. Alright, that's a 1. And the constant 0.5 degrees Celsius per molality. So multiply all of this, add a plus 100, and that's going to go ahead and give us our answer. So our elevated boiling point becomes 101.5 degrees Celsius. That is the answer for example 8. Next, let's go ahead and take a look at example 9. In this problem, they ask you, how many grams of calcium chloride, CaCl2, are needed to elevate the boiling point of 250 grams of solvent to a temperature of 109 degrees Celsius? Alright, so in this problem, we're going to go slightly backwards where they're giving us the boiling point. They want to know how many grams we should add. So the first thing we're going to do is go ahead and plug all the values that we have here and solve for the molality. Once we have the molality, we're going to solve for the number of moles. And once we have that, we're going to go from moles back to grams, and that will give us our answer. So let's go ahead and start plugging in all the numbers we know. We know that the elevated boiling point is 109 degrees Celsius. We know the normal boiling point of water is 100 degrees Celsius. The I for CaCl2, calcium is a metal, chlorine is a non-metal, so we'll ionize. So the Van Hoff factor for CaCl2 is I equals 3. So I'm going to plug that number in. Molality I do not have, but I do have the constant. It is 0.5. Alright, so I'm going to go ahead and isolate the m. So I'm going to subtract both sides by 100. So I end up with 9 equals 3 times m times 0.5. Multiply both of those. 1.5 times m. And I divide by 1.5 to get the value of the m. So it's going to go ahead and be 9 divided by 1.5. It gives me 6. So the molality is 6. So now we have the molality, we can go ahead and use that to go ahead and solve for the moles. Alright, so for formula for molality is moles over kilograms. Alright, so I'm going to slide over the kilograms here. So it's really kilograms times molality will give me my moles. Alright, now I have the molality here, the kilograms. Let's take a moment to talk about those. We have 250 kilograms of solvent. So to change those from grams to kilograms, we divide by 1,000. So it'll look like this, 250 grams. 1 kilogram is the same thing as 1,000 grams. So that gives us 0.25 kilograms. All right, so that will be the value that we'll plug in here. The molality goes there, and now we'll use that to solve for the moles. So it's going to be 0.25 kilograms multiplied times 6 molal. So that'll give us 1.5 moles. Great. Now that we have the moles, all we got to do is get the moles and go from moles to grams to get our answer, which is how many grams of CaCl2. Alright, so we're going to need the molar mass of the CaCl2, the calcium chloride. There's 1 calcium, 2 chlorines. Calcium and chlorine, this is 35.5 and 40.1. So the molar mass. So that'll give me 40.1 and that'll give me 71. So add them together, 111.1. That's the molar mass of the calcium chloride. So we're going to use that. Now we need to change the 1.5 moles to grams. So it'll look like this. 1.5 moles. For every 1 mole, there's 111.1 grams. So we plug that into the calculator. And we get the answer, which is, might round it up a little bit, 166.7 grams. So you would need 166.7 grams of the CaCl2, the calcium chloride, to solve in 250 grams of solvent, so that way we can get an elevated boiling point of 109. Alright, that takes care of example number 9. This brings us to the end of lesson 3 of unit 7. Thank you for watching.